Yes, class, am I audible to all of you? Alia, Austin, Humam, Tariq, Shahid, and Chavez. All right. See, in the last class, we started with EM waves. We were there at, we were doing the properties of EM waves. We couldn't complete it. Let us just complete all the properties. And I told you displacement current is also left to be discussed. Now, see, electromagnetic waves, what all we have studied about it, that electromagnetic waves, these are the waves which are propagating in under the influence of electric field and magnetic field, and both electric field and magnetic field both are mutually perpendicular to each other as well as perpendicular to direction of propagation. This we discussed. These are the formulas which on the basis of which we'll be practicing questions also today. E is equal to E naught sine kx plus minus omega t. So we'll see how questions come from this part. Spectrum I had asked you to study. I'll ask you today also. I told you that I'll ask you questions based on electromagnetic spectrum. So that I'll ask it today itself. Now, properties of electromagnetic waves. Electric field, magnetic field, and direction of propagation, these are perpendicular to each other. Ratio of electric field and magnetic field gives the speed of light if it's its peak value, otherwise normal speed if it's a normal value. Then C is equal to 1 by under root mu naught epsilon naught, that is the permittivity's value. And if it is traveling in a different medium, then V is equal to speed of light divided by under root epsilon r mu r. That is the relative permeability. Refractive index, optical phenomena, this we'll do when we'll start with ray optics. You have a lot of syllabus on refractive index. You have to discuss optical density and everything there we'll discuss. Now, energy density is something which you have to remember. Remember, we have done this density word so many times. We did current density also. Current density, we did electrical density also, electrical energy density, remember? So electrical energy density means this part, this we have done, we have derived it also. And I told you that that is important, that will come again. Yes, what was the value of electrical energy density? Two things I told you that we did in the form of question. One was force, which we did, and second was electrical energy. Yes, class. What was the formula of electrical energy? Energy density we have done. Half electric field square into epsilon naught. No, not VI, Chavez. Chavez, this VI is not density. That is simply, you are telling me the formula of power. V into I, that is power. All right, Chavez, this Chavez is correct. Energy density means energy per unit volume. If you people remember, we started this derivation, then capacity. And revise this one, the derivation is important. So electrical energy is basically, electrical one is half square of electric field into epsilon naught. This is the formula of it. Half into E square into epsilon naught. This is the formula. Now, similar formula you have as magnetic energy. What is meant by magnetic energy? Now, how will you remember this? Half will be there, half was here, common. Electric field is written in electrical energy. We have to write it in magnetic energy. So if electric field is E, which energy will use? What will we use here? We'll use magnetic field. If electric field is there for electric field, here you will be very good, Chavez. We'll use B. So E square will become B square. Now see, here epsilon naught is getting multiplied, just 1 point of difference. Here mu naught will be divided. So do not multiply it, please divide it. So electric field, energy, electrical energy density. Energy density means what? Energy density means energy per unit volume. In 1 meter cube, how much energy is being stored? In 1 meter cube of a particular substance, if you're taking, or any volume, in that area, be it the plates, parallel plate capacitor, If we are talking about resistors, anywhere, electrical energy density means wherever energy can flow. So if you take 1 meter cube, how much energy is present in that 1 meter cube? That is electrical energy, half E square into epsilon. All right, this is electrical energy density. And class, this derivation, when we did in the class also, that time also I told you that this is very important, half E square into epsilon. Secondly, we have magnetic energy. Now see, magnetic energy, this is the formula which you have to remember. And how is it derived? This is derived in the same manner. We take the energy, we take the volume, we divide it. But thing is that this is not in your syllabus, the derivation of magnetic energy density. These are not just energies, these are energy densities. The main heading is this, energy density. So these are energy densities. So these are individual energy densities. When we are talking about total energy density, because that was just the concept of electric field, electrostatics and magnetostatics separately. Right now we are talking about EM waves, and EM waves, these are moving, these are propagating under the influence of both electric field as well as magnetic field. So total energy density, you will consider electric field energy density and magnetic field energy density, both of them. So when we are talking about total, add both of them. You have electrical one, you have magnetic one, just add both of them. So this becomes half E square into epsilon naught plus half B square divided by mu naught. Just keep this in mind that permeability will not be multiplied, permeability will be divided. Now see, when we are using the term E square, B square, what is meant by this? We have studied ERMS also, we have studied E naught also. So what exactly is it? This is actually RMS value, RMS value. So instead of writing this, I can write this as half ERMS square epsilon naught plus half BRMS square divided by mu. And what is the formula of ERMS and what is the relation of ERMS with E naught? This. ERMS is E naught by root 2. Similarly, BRMS is also B naught by root 2. So what will their square become? E naught square by 2, B naught square by 2. So let us put in the value of ERMS and BRMS in terms of their peak values. So this becomes, this will become half. So ERMS square, that becomes E naught square divided by 2 into epsilon. Plus this becomes half BRMS square. So instead of BRMS square, you will put B naught square divided by 2 into divided by actually mu naught. Fine, this is how we'll write one. All right. So what is the final formula? Because most of the questions you have it in terms of the peak value. That's why we are writing this separately. This becomes 1 by 4 E naught square epsilon naught plus 1 by 4 B naught square divided by mu naught. That's it, what you have to remember. This is the main total energy which you have to remember. I'll discuss momentum with you. Momentum also is a little lengthy topic. First, write this down, energy part, then I'll discuss momentum with you. Because here momentum, here energy densities, you can look, this is not so simple and straight, or whatever we have done, it is as it is. No. You can see here is there is a modification. Our final formula was also different, and this formula you haven't used anywhere. No, 1 by 4 E naught square and all you have not used. Similarly, momentum's concept is also similar but different, and you people have already studied the concept of momentum in class 11th. So first note this down, then I'll discuss momentum with you. See, momentum which you have studied in your class 11, force is rate of change of momentum. This was the Newton's second law. You must have done this in class 11. Now, see, the formula of momentum that we are going to use for EM wave. This is derived. Actually, there's a derivation for this, but derivation you people need not do. Even you'll just get questions based on momentum. All right, even the formula is also not used so much, but you should be aware of the formula. Momentum here for electromagnetic waves is the ratio of energy to the speed of light. Energy we have studied above. Just before momentum, we have studied the energy. So ratio of energy and speed of light. So formula is very simple. P is equal to energy by speed of light. So this is energy and this is speed of light. All right, energy and speed of light. Now, see, coming to Newton's law, which I told you, you have studied. So what was Newton's law? Newton's law was momentum, which was changing with respect to time. Now, why am I discussing this in detail is because you will get questions. So just pay attention over here. Then you can copy it down. I'll give you time. Force is equal to momentum per unit time. Now, when you are going to calculate the net momentum, see, this is an absorbing surface. There is a reflecting surface. So when this is the initial condition, all right, this is the first condition. Electromagnetic wave, this has struck the surface. This has struck your absorbing surface. Fine, this has struck the surface. So initial momentum is P. P1 I have chosen. This is the initial momentum P. Then what happens? If it's a reflecting surface, if the surface becomes a reflecting surface, then second case occurs. That is, wave will exactly rebound to itself. It was coming, it will just rebound exactly to its path. So this will be the second momentum, P2. All right. Now direction will be exactly opposite. It will retrace its path. These are properties of electromagnetic waves, and this part, no, this specifically reflection part, this we'll study in ray optics. You already have a whole unit for reflection, refraction, every phenomena. So there we'll see. So a ray of light came, it got bounced exactly on its direction. So initially velocity was downwards towards the reflecting surface. So momentum was also downwards in the first case. In the second case, velocity is directed upwards. So momentum is also directed upwards, right? This is the case that is given to you. Now see, when we are taking the net momentum will be the initial and final. You will take the differences between them. This is P1, this is P2. This is how you will take the relative momentum between the two, right? Now see, here what is happening, both are having exactly opposite direction. So you have to consider sign convention here. So one take one as positive, take other as negative. Suppose I have taken downwards as positive and I have taken upwards as negative. So P1 will become plus P and P2 will become minus P. Right, simple. So what I want to tell you is that when you will put the value of P1, this will be P, this minus sign. But when we're talking about P2, this becomes minus P. So what is the net momentum? Net momentum is 2P. So what is the force? Force is 2P divided by T for the reflecting surface. See, this is like relative, the concept of relative velocity. Our vehicle was moving, the first speed was 5 meters per second. V2 second was moving with a speed of 3 meters per second. Both are in the same direction. Then what will be the relative velocity between them? 5 minus 3 or 3 minus 5, depending which magnitude will be 2 meters per second, right? But if the same thing occurs, V1 is along this direction with velocity 5 meters per second, but another car is in the exactly opposite direction with velocity 3 meters per second. Now, will you take it as 5 minus 3? No, you will have to consider the sign convention. So if this I have taken as plus, this I have taken as minus. So 5 minus minus 3. That will give 5 plus 3, which is 8. So 8 and 2. Here the answer that I am getting, this is 8 meter per second. And here the answer that I am getting, this is 2 meter per second. This is 8 meter per second. So there's a lot of difference between the two. Right. So here what exactly you have to remember as a conclusion, that when a ray of light, or not a ray of light, when the electromagnetic wave strikes an absorbing surface, strikes a reflecting surface, and it gets reflected, some force becomes double because momentum doubles. This conclusion you have to remember. All right, that momentum will double itself. Otherwise, what it seems like, if it is coming and it is getting reflected back, then both will cancel each other, net momentum is 0. But when you're putting the sign convention, you are seeing that 2 times it is becoming. So how is it becoming 2 times? Simple. You people have done these types of concepts in your class 11th also, relative velocity, motion in a straight line and everything. You have already done this, right? So P1 and P2, here just remember the conclusion that force will also become double because momentum is becoming double, twice. This is the conclusion which you have to remember. Last property is the property of intensity. How do you calculate intensity? Intensity is defined as energy per unit area per unit time. Energy per unit area per unit time. If you people can identify, can any one of you tell me what is meant by this? Energy per unit time. Yes, yes, Chavez, very good. Power, very good, Shai. This is power. So what, which is the other formula of intensity that you can mention? That is power per unit area. No, the definite, this intensity's formula, you can mention it as power per unit area. Coming to the SI unit, same thing. This becomes joules. Area's SI unit, energy's SI unit is joules. Area's SI unit, when you're talking about area's SI unit, this becomes meter square. And when we are talking about time, time is seconds. This, instead of writing this unit, you can identify joules per second. What do we write joules per second? What? So the SI unit can be watt per second. This formula will also be used. And this SI unit, this will only be used, whether you use this formula or this formula. Because joules per second, we usually do not write, because 1 joules per second is already equal to watt. Note it down. 2 questions we'll see then after this. Questions we didn't do, no? So we'll discuss it. Write it down from here. Yes, Austin. Please correct this. Not watt per second. Watt is already there for joules. So we have watt instead of joules per second and meter square. Yes. Watt per meter square. From here also you can write this. Now see, this question says that a plane EM wave of frequency 25 megahertz travels in a free space and time. Okay, space and time. Electric field is given as 6.3 J cap. What is the magnetic field at that point? See, electric field you have, you want to find out the magnetic field. You already have the knowledge about the speed of light, its relation with magnetic field, its relation with electric. So just use that formula. So this makes it electric field is 6.3 J cap. Speed of light is 3 into 10 to the power 8 meter per second. This is Newton per coulomb, and magnetic field you have to tell. So this becomes C is equal to E by B. So B is equal to E by C. So my value of magnetic field will be 6.3 divided by 3 into 10 to the power 8 J cap Tesla. So this will become 2.1 into 10 to the power minus 8 J cap. Yes. Very easy short question. Quickly write this down. Then this question I want to discuss. This last question before we start with displacement current. This is an important question. These types of questions come a lot in your exams from EM waves. If a question has to come. And for your entrances also, this is very important. Just quickly write this down. See, this question has given you the value of magnetic field along y-axis to be 2 into 10 to the power minus 7 sine 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11t. You have to tell wavelength, frequency, and you have to tell the expression for electric field. When this equation is given to you, By is equal to 2 into 10 to the power minus 7 sine 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11 t. This is equal to main equation. Remember, B is equal to V naught sine kx plus omega t. This was the equation with which we had started also the class. So now you know what are all the, see here only wavelength and frequency, these are asked to you. You can be asked what is the magnitude, what is the amplitude of the magnetic wave. So amplitude is B naught, which is 2 into 10 to the power minus 7. This is the amplitude or the peak value. Fine, if this question comes to write about the amplitude, peak value, highest value, maximum value of magnetic field, then this is directly the answer. You don't need to perform any calculation in this. Second part, it says wavelength. If wave number was asked, then also you would have directly used 0.5 into 10 to the power 3. Omega angular frequency 1.5 into 10 to the power 11. But none of these are asked. You are asked wavelength. See, when we are calculating wavelength, I told you there's a relation between the wave number and the wavelength. For the first part, K is equal to 2 pi by lambda. So lambda will be equal to 2 pi divided by K. So 2 pi, or let me write down the value of pi itself. This becomes 2 into 3.14 divided by K is 0.5 into 10 to the power 3. So this will be around 12 point something, 12.12 something. This should come around into 10 to the power minus 3. This, please write this much meters. Secondly, it has asked you to calculate frequency. So see, 2 pi mu is equal to omega. So frequency will be equal to omega divided by 2 pi. So omega is also given 1.5 into 10 to the power 11. And this is 2 into 3.14. This much, whatever answer comes, I do not remember the exact answer. This also will be around 2.5 something. This should come. Just calculate. This much hertz. This is the answer for the first part. Like this only you have to solve whatever is asked, whatever you already know, you will extract it from the equation, you will put into the formula and check. That's why we did everything in the previous class. All right, now when it says expression for electric field, see, the only difference when we are talking about electric field that will come is, first the class, this magnitude, right? So again, C is equal to E naught divided by B naught. So E naught is equal to C multiplied to B naught. 3 into 10 to the power 8 multiplied to 2 into 10 to the power minus 7. So this becomes 6 into 10, 60, right? 60 Newton per coulomb. So your equation, we are writing along y-axis only, because the rest of the details in which axis is electric field propagating, that all we do not. Nothing is mentioned also. Write an expression for electric field is just given. So we also have no idea about the rest of the things. So only this is going to change. Rest just copy it down. Sign, because value of K will also be the same. K was how much? 0.5 into 10 to the power 3. 0.5 into 10 to the power 3x plus omega t, 1.5 into 10 to the power 11 t, this much of Newton per coulomb. That's how you have to write it. Write it down, then one last topic will be left. Done.
Yes, ma'am.
See, now coming to Maxwell's displacement current. So if we talk about current electricity, we have seen how circuits were constructed. So basically there was an experiment that was done by Maxwell. So he took wires, a series of battery he took, and here was the switch. Now at the ends of these, the way we connect capacitor, we also connected to spherical circular plates capacitor, not spherical circular plates capacitors. So usually, we write capacitors like this. So that has only been depicted, but in a circular manner, because these were the circular plates that were taken by. So this is actually capacitor only. Now there we have taken, not we, actually this entire experiment was done by Maxwell, and the conclusions were also done by him. The entire formula also has been derived by him himself. So there was one point taken over here. This, see, current was allowed to flow in the circuit. This is closed, switch is closed, so obviously current will flow. If switch is closed, current I will be flowing over here. So current I flows from here, entirely current I is flowing. Now, if I choose a loop here, there's a circular loop that was chosen, C1. So what was observed? B dot dl closed integral for this C1. If we are talking about this C1, this is equal to mu naught I. Can anyone tell me according to which law am I writing this? We did a law on the basis of which I have written this. This we have done.
Ampere circuit law.
Yes. Ampere circuit law, not Gauss law, Chavez. Ampere circuit law. Gauss law is there for electrostatics. Good. Ampere circuit law. So this was observed. Then one more was taken between these two. That was C2. When C2 was taken, it was observed that closed integral of V dot dl for this C2, this comes out to be mu naught into I, and there isn't any current between the capacitor plates. We know how the charges transfer. The process of induction occurs from one positively charged plate to negatively charged plate. The charges move and on. But in between them, current is actually not moving. So this becomes current here becomes zero. So this entire derivation, this becomes zero when we are choosing a second circular loop in between the plates. So if a circular region is being selected or within the wire where current I is present, B dot dl is equal to mu naught I. But if this same circular loop is chosen between the circular plates, then this is taken as zero. Fine. Now, when we are talking about the net total current that are occurring, so yes, the result of Maxwell is inconsistent with Ampere's circuital law. We can see the conclusions that were derived by Maxwell, these are now not matching with Ampere's. Here it was initially, right? This is exactly Ampere's circuital law. You people have only answered that this is Ampere's circuital law. But here what is coming? Closed integral of B dot dl, this is equal to 0. This is coming to be 0. This is not matching Ampere's circuital law. Ampere never said that a closed integral of a closed line integral will ever be equal to 0. It is always mu naught into I enclosed. This is directly 0 over here. So there is an inconsistency observed. Reason was that because here one more current was flowing in between these. That was known as the displacement current. This I'll tell you. First, do one thing. Write it till here, then we'll do the formula part. Otherwise, you'll mix it up. First, write it down, then I'll tell you. First, write it till here about the inconsistency, then I'll discuss it. written. Now see, so what have I told you? Yes, result of Maxwell is inconsistent with Ampere's circuital law. Now see, in order to get the net current of the total circuit, right? The net current means the current of the total circuit. We have to find out which current is flowing between the plates. Otherwise, circuit is interrupted. There is no current flowing, but this is not possible. Current is there in our circuit. So Maxwell added a term that was displacement current. He said that there is a current that is flowing within the circuit. This is known as conduction current, which is the normal current which we have been studying. Then he added a term displacement current. Displacement is current is not flow of charges that is occurring per unit time the way you have studied. Displacement current, it's basically flow of electric field with respect to time. Electric field that is occurring, induction that is occurring with respect to time. That current we are calling it as displacement current. So formula is also completely different. This is the total. This is now the I enclosed. And formula of displacement current is epsilon naught d phi over dt. Because this is directly proportional to the electric flux that is flowing. I told you electric field, electric flux, whatever is crossing per unit time. So when you put it in the main actual Ampere's circuital law, when you keep it under actual Ampere's circuital law, see, this will become, this becomes, yes. So I enclosed, when I'm talking about, you have two current now, conduction current and displacement current. Displacement current you already conduction current you already know. Displacement current is something that has to be added up. So integral of B dot dl is equal to mu naught IC plus I D this time. So what is your resultant net formula? Resultant final formula is closed integral of P dot dl. This is mu naught. Conduction current is as it is, epsilon naught d phi over dt. So this is the formula of, this is the modified Ampere's circuital law. This is the modified Ampere's circuit law which you will be using. All right, this is the entire one. Now see, how can you further modify it? D phi, this you can write it as rate of charge, basically charge divided by epsilon naught. Flux is equal to charge enclosed by epsilon naught. This is which law? Flux is equal to charge divided by epsilon naught. Class, which law is this? Gauss law. You people have forgotten Gauss law even. Not Faraday law, Chavez. Flux is equal to charge enclosed. Remember this sentence? You people have done this. Gauss theorem, we did it. That the charge, the net electric flux enclosed within the body is 1 by epsilon naught times the charge enclosed in it. So you people have done it. So this is Gauss theorem only. Now at this stage, when we are completing the first book, you people are not remembering Gauss theorem, then we cannot move forward. So yes, I was saying you can replace this when we are writing this closed integral of magnetic field. This becomes mu naught epsilon naught. Instead of d phi, I will write it as dq over epsilon naught, and dt was already there. So epsilon naught will be cancelled, plus conduction current, which is already there in your circuit. All right. So finally, what are you getting? Finally, you are getting this closed integral of B dot dl is equal to mu naught I, right? This is I, where your current is now equal to C. How have we concluded this? dq over dt, this dq over dt, this is equal to I, right? Which is now consistent with Ampere's circuital law. Conduction current was already there in your circuit. Conduction current was already there. Right now, I'm not even talking about conduction current. We can even remove it. I'm just talking about the main second one. I'm talking about the displacement current, the second loop, C2 I'm talking. This is C2. So there's no concept of conduction current. Now you can see C2 is consistent. once we use this formula, no, d phi over dt, displacement current is equal to d phi over dt, and then we use Gauss theorem, you can see current is coming back in your circuit. Now this is saying this is now consistent with Ampere's circuital law. This is the consistency with Ampere's. Write it down. This is clear. See, initially this was coming something else. Why? Because there was a lack of displacement current, which was actually present. So it is the current that comes into existence in addition to the conduction current whenever the electric field and flux change with respect to time. Current. Fine, write down from here. Those who have completed, you people can leave now. Just listen one thing before leaving. Tomorrow, I just have to discuss one question and the properties of the displacement current that will be dealt in just half an hour or even less than half an hour. So after that, no class, whatever doubts you people have from the entire first book, all the lessons from electric charges and field till EM waves, please share your doubts, take the picture from wherever you have your reference books, NCRT, your question papers which are going in the school, Learnivio questions, assignments, any question, all the questions, please collect it, share it to me before the class tomorrow on WhatsApp. It's better if you share it today only, because then otherwise during the time, no, during the class when you will send the question, then I'll read, then I'll solve it, it will waste the time. So at least I'll have the question prior, so I can just call out your names and the questions will be done. So doubt session is there after the class. So please, whatever doubts you people are having, I'm again repeating, share it to me on WhatsApp before the class. Anytime, it's not necessary today, to any time before tomorrow's class starts. So at least during the class, this exchange of question and WhatsApp using, and this doesn't happen. Only I'll be reading your questions and whatever doubts you people have collected. Those unanswered, I think Chavez, one time you had also sent me a question which I didn't answer. That every question which you people have, tomorrow we'll discuss that. All right. So now you people can leave. Tomorrow we'll meet. Thank you so much.